has indicated to us that it's probably a good idea to start transitioning this kind of technology to industry. And that's what we are accomplishing now with our collaboration with our small business partner, NKDS Technologies. They had actually created the first real ballistic armor prototype of the transparent materials made by LBL and combine them with more traditional transparent armor materials. And as you see on this photograph, the transparency of these kind of stacks is very high. And they also performed the live ammunition test. In this particular case, it was a 7.62 39 millimeter projectile, which is very typical for many parts of the world: Iraq, Afghanistan, Africa. And as you see, we have no penetration for a relatively thin stack of the materials which are utilizing the LBL technology. Just like in the laboratory test, in the back of the plate, we see just a small indentation made by the bullet. And so all that leads us to the question how we can scale up the production of this kind of composites. And this is also an important problem that we are trying to solve together with NKDS Technologies. The way how we envision it, we will initially create individual sheets of LBL and then consolidate them together to produce thicker sheets. This kind of approach allows us greater control over all the properties of the final composite materials, because we can combine elastic sheets, stiff sheets, and create their new geometrical micro and nanoscale features, which eventually would lead to the reduction of the weight of this material. We demonstrated that for both carbon nanotube films and clay films, and as you see for clays, these kind of stacks retain their transparency, and now they can be directly used into the production of the transparent armor materials. Just a quick point about some science aspect of that. These consolidated stacks can be also used for very fundamental studies, how the deformation occurs upon the impact of the projectile, because this is very difficult to investigate by other methods. And here you see that we can image it by using different type of fluorescence, how the cracks are penetrated into these materials. And indeed we see that the interfaces take quite a lot of load in this impact deformation. Speaking of scaling up and how we can transition from the lab to the industry, we also need to think about acceleration of LBL. I pointed out that this technique does require multiple deposition cycles. It provides the control over the structure, but it also makes it more time consuming. There are a number of robotic devices, and a lot of them are developed in Europe. Quite a few of them are also developed in the United States. And all of them, they basically replicate this basic idea that you take a slide, immerse it into one beaker, then rinse it, immerse it in the other beaker, and the robotic arms moves that slide from one beaker to another. It takes time to move this arm, it takes time to deposit the film, and we thought that we need to transition from this kind of robotic devices to something new. And many of them, for instance, nanostrata, are very widely used in the research lab. But when we want to create the technology for the industry, we need to come up with something else. And together with Nico, we developed a new type of LBL deposition robot, which they called Turbo LBL. Instead of the robotic arm, here we used the rotating drum. And each component, for instance, clay and polymer, sprayed on different sides of the drum simultaneously. And so what this kind of deposition system allows us to achieve, we don't have any waste of time on moving the slides by the robotic arm at all. It all occurs at the same time. We also have only one moving and simple part, which is the drum, which makes it very reliable. We also have very overall, this results in 1,000 times acceleration of the deposition compared to the traditional LBL technology. So both Nico and I are very excited about this kind of deposition system, and in this little video you see how actually this spray happens. This is the spray of the clay component during the rotation of the drum, and of course, I mean, the whole system is controlled by the computer. We'll also see quite straightforward direction for the scale up of this technology, including from this batch process to the roll-to-roll type of the devices. So this also brings up the question, what are the other potential directions besides the transparent armor for this composite? And we think that the blast armor should also be included here as a very interesting possibility, and very important possibility too. The traditional blast armor protection technologies are heavily relying on the steel plates. MRAP vehicles developed not long time ago also increased the blast protection by using the V shape of the hull that deflects the blast. These vehicles, they saved lots of lives, and yet they might be improved further. They're quite heavy. This weight is not just a simple the heavy weight of the vehicle results in the number of problems. For instance, the road collapse. They have high consumption of the fuel. The V shape of the hull results in the high mass point of the vehicle, so there are many instances of the rollover of MRAPs. And so it would be very nice to improve them further and to possibly reduce the weight of the vehicle. That can potentially can be done with the composite armors. There are also quite a lot of problems with the blast protection of the soldiers as a part of their uniforms. Helmets do not have adequate performance for the blast protection. In fact, there are a few indications that polyurethane foams, which are traditionally used for the blast protection of the troops, they actually exacerbate the injury of the head during the blast. It's also heavy. The weight problem is tremendous for all types of the armor. In this case, we also need to be concerned with the heat because the thick film of the foam makes it very uncomfortable to wear it in the hot climates. And so in this respect, we can certainly state that the new blast protection materials are very much needed for the military and have to be developed. And in this perspective, new type of advanced composite, maybe from LBL or maybe by other techniques, they represent quite a lot of interesting possibilities. The absorption of blast impact at the interfaces intrinsic for such composite can reduce the weight and can prevent accumulation of the heat as well, because we are transitioning from the foam type of the materials to the materials which are easier to transmit the heat. In this respect, I'd like to point out a very interesting new type of nanoscale component such as graphene oxide or graphene. It is very inexpensive, it's also very strong, and here is the example of one of the graphene oxide composites which had been made by Nika Technologies in collaboration with my group at the University of Michigan. And so the design of new blast protective materials have intrinsically include the nanometer scale features, micrometer scale features, and therefore we really need to rethink and develop new kinds of composite manufacturing technologies, as well as the methods of production assembly of these blast protective materials. Transparency is also quite significant here, because the latest studies indicate that transparent shield for the helmet would dramatically increase the blast protection of the troops, the blast protection of the troops. With this, I'd like to thank you all for your interest. And if you need more information, we'll be happy to give it to you by email or by any other means that you consider suitable. Thank you very much.
Great job.